Hi everyone. This is a proof of the Pythagorean theorem using similar figures. So I took this diagram right here, which consists of three similar figures, and I separated them. So we are given that all these three triangles are congruent to each other. And we have that here in this similarity statement. And we are being asked to prove the Pythagorean theorem, basically. AC, which is this distance, this leg, squared, plus BC, which is this leg squared, equals AB, which is this distance squared. And we're going to prove the Pythagorean theorem using similar figures. Okay, so the first thing I did was separate the figures, and I wrote some useful proportions. Okay, so let's look at this proportion here. AC is to, let me dot this in, AC is to AB, which is what I have here, AC is to AB, just as AD is to AC. So that's where this proportion comes from. Now let's look at this proportion. BC is to AB just as BD is to BC. Okay? So I use the small one with the large, and I use the medium with the large to write these proportions. But you should actually recognize what these proportions are called. Okay, you see I have AC here and AC here, which is this side here. And then I have the whole hypotenuse, and then AD. That's what I have here. So you should recognize that this is the geometric leg theorem. That's what this proportion is for. And this proportion here is the geometric leg theorem for this one right here. Okay, because BC is going to be equal to, BC squared is going to be equal to the whole hypotenuse times the related leg BD. So that's where these two proportions came from. All right, so let's go ahead and begin our proof. Let's start with what is given. And I've already written it out for us. Okay, we're given that these three triangles are similar. Okay, we can, because these triangles are similar, we can write these proportions. Okay, so that's what we're going to do next. AC over AB equals AD over AC. So that's one of them. BC over BA equals BD over BC. And the reason, similar figures are proportional. All right, 3. I'm going to go ahead and take the cross product of this proportion and do the same thing with this one here. So AC times AC is AC squared equals AB times AD. I'll do the same thing here. BC times BC is going to be BC squared equals BA times BD. And this is simplifying. We just simplified. Okay, so the next thing I'm going to do is I'm going to add this segment plus this segment, because these are the segments of the triangle. AC, right here. This is that leg, AC is one leg, and BC is the other leg. I'm just going to add those legs, okay? So AC squared, so one leg squared, plus the other leg squared. Okay, that's going to be equal to the sum of this plus this, because we took this and added to this. Well, that would be the same thing as taking this and adding it to this. Okay, so let's just add these two together. So AB times AD plus BA times BD. And that's just segment addition. Okay, fine. I'm going to try to simplify what I have. So AC squared plus BC squared. I'm going to try to simplify this side. Okay, they both have the same factor, AB. This is AB. So I'm going to factor out AB. When I factor out AB from here, I'm still left with AD. Plus, when I factor out a BA from here, I'm still left with BD. So this is the distributive property. All right, so now we have AC squared plus BC squared equals AB. Now, let's see if we can use substitution for this part right here. AD plus BD. Let's see what that looks like. AD plus BD. Okay, this is the segment we're talking about. AD plus BD. Wasn't that BA? Isn't that all of BA? So can't we just say, oh, okay, AD plus BD is really AB. So we can replace it with AB. So AD plus BD is the same thing as AB, substitution. Okay, so this is substitution. Let's simplify. So we have AC squared plus BC squared equals AB squared. Simplify. And that's it. That's exactly what we were trying to prove. AC squared plus B squared equals AB squared, which is the Pythagorean theorem. Okay, so A squared, we have just proven A squared plus BC squared equals AB squared, using similar figures. All right, let's go to our next proof. All right, so this is our second proof. Okay, we're trying to prove this, which is the proportionality theorem. And that's what we're trying to prove. The proportionality theorem says that this piece here, the ratio of DA over CD, is the same thing as the ratio of EB over CE. Okay, to prove the proportionality theorem, what we're going to do is show that these two triangles are similar. We'll show the small triangle CDE is similar to the larger triangle CAB. If we can show these two are similar, then we can write a proportion to relate those two, and then rewrite the proportion so it looks like that. That's it. That is the plan. All right, so let's get started. Number one, we'll start by writing what we're given. AB is parallel to DE. And that's given. Two. Well, if the lines, if AB is parallel to DE, that means this angle and this angle are congruent, and this angle and this angle are congruent. Because if they're parallel, these are corresponding angles. So we can say that angle CDE. CDE is congruent to angle CAB. Also, angle CED is congruent to angle CBA. Let me fix this. This is E. CE. CED. All right, so the reason corresponding angles are congruent. Okay, well, that's enough to say that these two triangles are similar because they have this angle in common and they have this angle in common. So by the angle-angle similarity, these two triangles are similar. So we can write that statement. Triangle CDE is similar to triangle CAB by the angle-angle similarity theorem. Well, now that we have established they're similar, I can write a proportion to relate the two. So we can say CA, the ratio of CA to CD, CA to CD is equal to the ratio of CB to CE. And the reason for that, similar figures are proportional. Similar figures are proportional. Okay, so now all we have to do is rewrite CA. Well, CA, isn't that the same thing as CD plus DA? So that's what we're going to do. We're going to replace CA with CD plus DA. CD plus DA over, we'll leave the bottom the same, CD equals, we'll do the same thing with CB. Because CB, this is CB, that's the same thing as CE plus EB. CE plus EB. And we won't change the bottom. Okay, and that's just segment addition. All right, so we're going to keep writing until it looks like what we want it to look like. Okay, so we're going to keep rewriting it until we get it to look like this. All right, so what we can do next is split up the fraction. Rewrite it, split it up. CD over CD plus DA over CD. We'll do the same thing with this one here. Split it up. CE over CE plus EB over CE. And that's just simplifying. Simplify. You're going to keep simplifying. CD over CD, isn't that 1? So we'll replace that with 1. 1 plus dA over CD. Okay, CE over C, isn't that 1 also? So we'll replace that with 1. EB over CE. And that's simplifying. All right, let's subtract 1 from both sides. So we'll end up with dA over CD equals EB over CE. And that's by subtraction. But isn't that exactly what we were looking for? Isn't that what we were trying to write? Do you see? This is the same thing as what we have here. All right? So basically, we proved that these two triangles are similar. And once we've established they're similar, we wrote a proportion to relate the two, and we just keep rewriting and rewriting the proportion until we made it look like this. And we're done. Okay, and this concludes this video on these proofs.